Spring ahead. Processing.
Honestly, yeah, he's still underachieving my class.
I like to do one really late. I like the notes. Right. Whenever you asked it, it was funny. That's actually all. And, basically, the questions. Oh. Uh-oh. Uh-oh. Lots. Which name judge you? Well, I think you better answer it. No, I don't have to know. Someone is the phone. Oh! All right, let's everyone breathe. Be okay. Which one? Standard deviation. Average. Yeah.
All right, are you ready?
Yeah. We never are.
So let me tell you. Hold on. Let me tell you something. Okay, you may or may not like your grade, but I don't want you to worry too much about it. It's out of 30 points, and one lab report is 25 points. So really, if you're doing well with lab reports, that's fine. We have so many lab reports. We have another quiz. We have a midterm. We have a final. We have so many ways you can get points. I don't want you to get disappointed with your grade, but at least you will have an idea of how to study and what to study and how to answer. Just a sec, guys.
Yeah.
And another thing, you're gonna see two colors at the top. So I went ahead and reviewed your exams and gave you a little bit more points. So instead of, going in and having a curve, I just thought, okay, we'll just go in and, give you a little bit more points, even if your answer is not complete. Yes, right.
So is that before or after those stats are what?
This stats is after I went in on the
Double check.
Yeah. So you'll see some of you got substantial points back. I just read your answers and I thought, okay, they are very close. They are getting it. So you got some points back. Okay. I'm gonna ask Nigel or Anderson to go around. All right, are you gonna be distracted if I'm gonna pass this along?
Yes. You can't just drop that and not expect us to not be distracted.
Yeah, it's a spooky time. This is the
I
biggest
should
scary
have
to give
waited
us a
till
Halloween.
the end, huh?
This is the biggest scary to give us a Halloween.
Oh, come on. I was very kind to you. You will see when you get your exam back. We're not so short. No. No.
It's fine, babe.
Oh, you got her.
Yeah. Gave me two.
Oh,
I got two.
okay. Again, don't get to step. I'll wait till this is over with before I start talking. Yes, Rachel.
I said you should have been at the end.
I should have done that at the end, right?
Trauma spiraling,
Huh?
trauma spiraling.
I know. Okay, but put things in perspective. It's only 30 points, you all. Study well for the midterm. It's 100 points. You want help?
Oh, this isn't. There you go. This looks more.
Okay.
I got it.
You still have more?
Yeah, these people are actually. Very good.
Yeah, umbrella. Okay. All right. Don't worry about it now. You can put it away. I posted the key. Okay, you guys, come back to me. Razi. Hello, buddy. I said your name. Come back. Okay. Review, and then I put the key on canvas. So you can look at, all of you look at the key, because nobody had perfect answer, obviously. So it's fine. We're not expecting perfect answers, but please look at the key to help you understand what the question was about. Okay. All right. And please don't hesitate to come to me if you feel that you deserve more points than what you were given. All right. Or if you have a question about any of the answers, please don't hesitate. Don't be shy. And I'm all ears if you come talk to me. Okay. All right. But again, put things in perspective, only 30 points. All right. Okay. Let's dive into finally atomic absorption. A lot of you have already done the lab, so you're familiar with the term. We're going to talk a little bit more today about principle and theory behind atomic absorption. Okay, so before we dive into that, let's try to remember something we talked about last time. All right, what is Beer's law? Your friend, yes, Mitch. Absorption is proportional to concentration. Very good. Well, I'll leave that for a minute. So absorption equal absorptivity, or your epsilon here. The distance, the concentration. There is linear relationship with the concentration, but only when your light is monochromatic. Only a singular lambda that you select for measuring absorption and determining concentration. All right. So how does a monochromator function in simple terms? Yes, Razi?
They explain that it made of many different wavelengths and spread them out into individual wavelengths, so you can use those to identify.
Very good. Yes, a monochromator take all of the light, diffract it into individual lambdas, and then you can select a wavelength. You can have a slit that selects a wavelength at a particular nanometer for absorption to be determined, as well as concentration. All right. And we answered this question already. In order for Beer's law to apply, we have to have a monochromatic light. Otherwise, Beer's law will not apply. Okay, very good. So with this, we can move on, talk about atomic spectroscopy. There's two forms: the atomic absorption, AAS, atomic absorption spectroscopy, And then emission, atomic emission spectroscopy. So we can measure the elements using two types of spectroscopy. The most common and cheap method is the flame atomic absorption spectroscopy, which you have in the lab and many of you already worked with. There is electrothermal AA, which is less used. We'll talk about it briefly. And then there is the flame emission, commonly used for two types of elements, sodium and potassium, and we'll talk about that. And then the ICP, which is inductively coupled plasma, atomic emission spectroscopy. We'll talk about inductively coupled plasma also later on. And then the atomic absorption or the atomic spectroscopy in general, we use it to determine mineral nutrients and also toxic elements like heavy metals. Okay, so you all are familiar with your periodic table. So everything in pink are elements that we can determine using atomic absorption. Are you embracing the atomic? Okay, the elements. All right, essential nutrients, essential for our body, and also toxic elements, several of them like lead, mercury, cadmium, nickel. And the USDA database, there are a lot of these elements you can find for different food products. You can find the content of them, like calcium, iron, magnesium, phosphorus, sodium, potassium, chloride, copper, and so on. Okay. So the principle we talked about absorption and emission last time. So absorption is, especially in this case, what we do is we measure the absorption of atoms in the gaseous state. So no molecules. So even minerals, if they are present in molecules, we use the flame to atomize it, to break the molecules, bond, and release the atom in a gaseous state. And then the atom gets excited by a source of light. And the electron, because it's electronic energy, the electron jumps to a higher energy level, get to the excited state. It doesn't stay there. It goes down to the ground state by emitting a little bit of heat and another photon of light. Now, if you remember, what would be the wavelength of the photon of light emitted? Longer or shorter than the initial one? So do you remember if energy is higher with longer or shorter wavelengths? Go ahead, Kristen. Shorter. The energy is higher with shorter. And then when we emit photon, after a little bit of dissipation of heat, is the energy, Caleb, higher or lower?
The lower energy, so longer wavelength.
Yes, exactly. So that's something you just want to remember, is that the energy of the photon that gets absorbed is higher with a shorter wavelength than the energy of light being emitted that would be of a longer wavelength. And then we talked last time about whenever you're running a spectroscopy with emission, you set your spectrophotometer to two wavelengths, the absorbing wavelength and the emitting wavelength. Okay. All right, so every element will have a spectra for absorption. So here on the axis here on the left, you see the absorption spectra, and then on the right, you see the fluorescence spectra. And you see the fluorescence is at the longer wavelength than the absorption. So every element had its allowable energy. Remember that we said every atom or a molecule have discrete energy levels. If the energy carried by the wavelength does not fit within its allowable energy level, it won't absorb. That's why we have an area where absorption happens or doesn't happen, depending on the allowable energy level within every atom and within every molecule. Okay, so does an atom have vibration or rotation energy? Do you remember? No, it does not, Tyler. Thank you. Because you don't have a bond, so there's no atom vibration of the bonds within atomic bonds within a molecule. Okay, you don't have that. And also you don't have atoms in a molecule rotating around its central of gravity. So no, there is no energy levels for vibration or rotation within an atom. So it's only electronic energy that the atom can absorb. Okay. So some of you did that already, and some of you will do that on Wednesday. So you prepare your sample. We'll talk about sample preparation in a minute. You have in solution, you have your elements or minerals of concern, the ones that you want to detect, and they are usually in a molecular form. Sodium chloride, potassium phosphate. You have different molecules. So what you do is your sample get aspirated or get sucked into the system, and fine mist is generated. That fine mist hit a flame or a plasma. So now you have solvent in very small droplets, and then you have your molecules that are made up of elements that you want to determine in these little droplets that are in the flame. What happens is your solvent evaporates. So you have vaporization of your solvent, and then the molecules, bonds are broken to get to those singular atoms. So now you have atoms in the gaseous state. These atoms get excited by a source of light. So you have your solution, and then you have the dissolution where your solvent gets evaporated. Then you have the flame energy, the heat from the flame will break down the bonds to give you the atom designated by M. And then you get the atom excited by a source of light. And that excited atom, you measure the absorption of light to get it to the excited state, or you measure the emission of light when it comes down to ground state. Now, some of you did the lab already. You know that you talked about making sure the flame is not too hot and not too cold, relatively cold. So if the flame is a little colder than it should be, you don't get enough breaking of the bonds. Do you remember, those of you that did the lab, if you don't break the bonds, what could happen? Do you get overestimation or underestimation? Molly? You would think logically underestimation, but it's actually overestimation. Does anybody remember why? If molecules are not broken, you get overestimation. You remember what those large molecules would do? They will scatter light. So the light that comes from the lab to a big molecule that did not get broken, it will scatter light, and less light will go to the detector. Then the detector will assume, since less light got to the detector, more light got absorbed. So you overestimate. Does that make sense? Okay, I will. So when you have large molecules that you don't break the bonds to release atoms, these large molecules, when the light from the lamp hits them, it will scatter light, and less light will reach the detector because the less scattered light are scattered. It's gone. And less light will reach the detector, so the detector with less light will convert to the absorption, assuming that with less light reaching the detector, you'll have more absorption. So you overestimate the concentration. So it's important that the flame is hot enough to cause the breakage of these bonds, but not to be cold in such a way that the bonds are not broken. That's one thing can happen. Now, if the flame is too hot, what could happen? Yes, they will ionize. So if the flame is hot, you would go from M to M plus, an ionized state. Now, what happened? Do you overestimate or underestimate in this case the concentration of the atom? Huh? Under, because ionized atom does not absorb like the same wavelength that your non-ionized atom will. So you get less absorption, more light gets to the detector because the ionized atom is not going to absorb at your selected wavelengths as much as your non-ionized atom. Because you always select lambda max most of the time. You select the lambda at which you have maximum absorption of your atom. And the ionized atom will not absorb maximum at that particular wavelength. Okay, so these are two cases for overestimation and underestimation, two opposite cases, too cold of a flame, relatively cold, too hot of a flame. So that helps you, whoever writing the report due tonight, is to think about your statements for your results to see which applies. If you have an overestimation or underestimation. There are other reasons for underestimation. Those of you that did the lab, was iron underestimated? In some cases, yes, Graham? Why do you think? Do you remember why iron could have been underestimated in your sample? Yeah, well, that's a good answer. Sometimes we're going to talk about your linear curve of your standards, and if your absorption is outside of that linear curve, either under or over, you don't get accurate determination. That's a good point. But I was thinking of something. Is iron a volatile element? It is volatile. It is volatile. So what, do you remember how we could use the ash that we used in the lab for your sample? What did we do? Ashing. What was that ashing about? You put the sample at really high temperature, incinerated it, or organic matter, it will be combusted and then have the minerals in the ash. So iron at 500 degrees C could volatilize. And then you end up having less iron in your sample, so you underestimate. Now, of course, we do the best we can in the lab to reduce that. So we ash at a lower temperature, we add nitric acid to enhance the combustion of organic matter and reduce the temperature and reduce the chances of volatilization. But still, iron and zinc, for example, are volatile elements. And then we're going to talk about what ashing that we would do to avoid loss of iron. Okay. So what you worked in the lab on, and some of you will on Wednesday, is the source of light. The source of light is a hollow cathode lamp that is commonly used in atomic absorption or flame atomic absorption spectroscopy. So the hollow, it's hollow because it's empty from inside and it has an inert gas, argon or neon, but it has two components, an anode and a cathode. So the cathode is the most important component of your lamp because it's made up of what? Those that did the lab, do you remember what the cathode is made of, Emily? Yes, it is made of, to be specific, of the metallic form of the element of interest. So iron, the metallic form of iron, calcium, the metallic form of calcium. So usually there is a lamp for every type of element where the cathode is made up of the metallic form of that element. But some lamps have two cathodes, like the calcium can have the magnesium in it as well. So the magnesium cathode. So one lamp can be used to analyze two elements. So depending on that, so you have to change the lamp. Those of you that did the lab, you put the iron first or the calcium lamp first, and then you changed it to the other lamp when you were done with that one particular element. So the importance of that is it emits that cathode when an electric energy hits it. It emits light in the allowable energy spectrum for that element. So only the energy levels that element is going to potentially absorb. And we select the one where we have the highest sensitivity. It can absorb at multiple wavelengths, but we select. So those of you that did the lab, you selected a specific wavelength for iron, and you selected a specific wavelength for calcium. And that would be the one with the highest sensitivity. Okay. There is another form of lamps, less common, the electrode-less discharge lamp. So here you don't have the current or electricity generated. Here you have radio frequency generator coil. So it gives you energy in a different form, but still it has similar principle for exciting the element of interest. And usually it's used with more volatile elements, such as mercury and cadmium. I need to have a new picture. We went through generations of atomic absorption unit. You can imagine the first time I taught this class was with this shady one over there, shady. It worked, but it gave up after a few years. And then we got another one that looked a little better. But now the one that's in the lab is a third generation. But I need to get a picture. Guys, remember, take a picture of our new one. Can you, or Saj, Miss Lady, can you do that for me? All right, and then I will update them. Okay. In order for you to generate the flame, some of you saw the flame already, which this is the compartment for the flame. It's ignited. There is an ignite here, but you need gasoline. So you need, and in this case, we use acetylene and we use air as a source of oxygen to light up the flame. Okay, and then the flame is lit. And the flame acts as your little crucible or sample compartment. In a spectrophotometer, you have a tube or a cuvette. So it is your cuvette, really, the flame, because that's where the sample goes in. So you have your sample in your little bottles. So usually between samples, we put water so that it doesn't dry out. And then we take this, there's a little capillary tube that you put in your little tubes, and the samples get sucked into an aspirator, and the aspirator gives you the mist, your sample in a mist, into the flame. It's a beautiful flame, and then the flame changes color. Did it change color for you once light hits and it's absorbing? It's beautiful. It changes color, and the sample is absorbing your iron or your calcium. They're absorbing light in that range, allowable energy range. So here's the illustration. So you have the lamp. It gives you the incident beam, and you have your sample aspirated into the compartment that gives you the mist into the flame that is generated by acetylene and air. with oxygen source. And then your molecules, due to the heat of the flame, break into atoms. The atoms absorb light in their allowable energy levels, and then the light leaving the sample compartment gets to the detector where you have a monochromator in there that selects the wavelength at maximum absorbance and convert that into, does the internal calculation and spits out the absorbance values for you. And you use that absorbance to calculate the concentration. And as a reminder, we follow Beer's law by selecting one wavelength at the highest absorption. So this is another illustration. So you can see here that the hollow cathode lamp or HCl lamp gives you energy at different wavelengths allowable for the element. And we select the one wavelength that gives you the highest absorption, highest sensitivity, and monitor that reduction in the light and convert it to absorption. So basically, you get the light, you get the absorption, then you select that one particular wavelength by a monochromator that goes to your detector. The AA in your lab, the atomic absorption in the lab, it's an old one, so it has one type of detector, which is the photomultiplier tube detector, PMT, photomultiplier tube detector. It's right there, photomultiplier tube detector. I think it says photomultiplier arrangement, but T is for tube. So the way it works is that when it receives the light hits a cathode and kicks off an electron. An electron goes off to an anode or dianode, and then it multiplies. More electrons are split off the surface, and it keeps doing that until the one electron becomes 27 electrons. So it's really amplifying the signal. So that's the name multiplier. So it multiplies the signal, so enhances sensitivity. So we can measure low concentrations. So this is the type of detector that the unit in the lab has. There are different types of detection, but this is the one we have in the lab. And it's a very common one. It's the photomultiplier tube detector. Okay. Just very briefly, we don't have that in the lab. This is another form of atomic absorption. You don't use a flame in this case. You use an electrothermal unit. Here, there is a surface that gets heat up, like a platform that you can heat up to really, really high temperatures, 2,000 to 3,000 degrees C. So here you put your sample in like a drop on the surface. Then you heat it up. The solvent evaporates, the molecule bonds break, the atom becomes in the gaseous state, and it goes above the surface, and then the light goes through, and then absorption happens. Now, it's more expensive than the regular flame, and you have less throughput. If you remember when you did the lab, those of you that did the lab, you're putting the sample and it's sucking continuously the sample, and then it's easy. You go from one sample to the other, to the other, to the other. Here, no, you have to do one sample at a time and then wait until it cools down and you put another sample in. So really low throughput, but it has higher, different advantages like lower threshold, so higher sensitivity, for example. Yeah, but because of it is more expensive and lower throughput, you don't see it very much in labs. You see the flame more, and now more and more the ICP, which I'll talk about in a minute. Okay, flame emission here, it's very, very simple. You don't have a lamp in this case. So the flame is the source of atomization and ionization. This is very important, you guys. Sometimes in a quiz or exam, I'll ask you what's the difference between flame atomic absorption and flame emission. The flame atomic, you have lamp as source of energy and ionization. Flame emission, you don't have a lamp. The flame is the source of atomization and ionization. So it is used for elements that ionize, at low energy. So these elements are sodium and potassium. So you don't need a lamp to ionize them. The flame itself can atomize them and not ionize them, sorry, to put them in an excite them, I want to say. Please scratch, no ionization, excitation. So it's a source of atomization and excitation. Please cross ionization if I said it multiple times. Sorry for confusing you. So here, your molecules break into atoms and the atoms are excited by the flame, the heat of the flame. No lamp is needed, okay? And this is commonly used for sodium and potassium because they have low excitation energy, okay? Not ionization, please cross that out. Low excitation energy. And usually instead of monochromator, you have a filter that filters the wavelengths of interest. It's very, very simple. And when you have a filter, it's called flame photometry rather than spectroscopy. If it says spectroscopy, that means you have a monochromator. If it says photometry, you have a filter for the light. Okay. And here we are measuring the emission of light. So in this case, because it's emission, so the atom is absorbing the energy and then we're measuring the emitted photon. So now I want to talk about ICP, which is inductively coupled plasma atomic emission spectroscopy. So inductively coupled, I'll show you it is coupled because you have an induction that happens. That's why it's called inductively coupled. And you have plasma that gets generated. What is plasma? It's the fourth state of matter. So you have solid, liquid, gas, ionized gas. Ionized gas is plasma. Okay. So the plasma in this case is used to atomize and to excite. No lamp. In ICP, you don't have lamp or source of energy that is coming through the lamp. The plasma itself atomizes, breaks down the bonds within a molecule and also excites. So how is plasma generated? You have argon gas, which has a lot of cations and electrons. So a lot of ions, basically. And what happens is you have that induction that causes this ionization to happen and the generation of plasma. Okay, so basically here you have radio frequency applied to copper coil to generate this ionization of the plasma. Here. So you have this is your plasma, it's very beautiful. So you have a coil here and the radio frequency that causes that heat to generate and ionizing the argon to generate the plasma. Okay, now you have plasma And then the same thing, you have your sample, you have a nebulizer or aspirator that converts the sample into a mist that goes into the plasma. So then what happens, your sample in the plasma, the solvent dissolves, the molecules break down to atoms, and the atoms get excited, and then they go down to ground state, emitting light. So all this light goes into the detector. There are different types of detector. This is a form of simultaneous PMT instrument. So all of these tubes, you have in here 7 tubes. So you have 7 PMTs. You can measure 7 elements at one time. So you can select wavelengths of 7 elements and direct them to those different PMT, and you can get a simultaneous reading of 7 different elements. Or, depending on the instrument you have, you can have 1 PMT, and what you do is you do sequential reading. So you would select one wavelength, measure the emission, then change the wavelength sequentially. So as the sample is going through the plasma, you change the wavelength, so you get sequential measurements. Or you get 7 measurements if you have 7 PMTs in your detector. This is obviously more expensive than having 1 PMT, but the most efficient is to have a charge injection detector. I'll tell you how it works in a second here. This is just an image. Oh yeah, sorry, yeah. So the radio frequency here, it shows you here. So there's the ignition spark. There's the induction zone. You have the coil, the radio frequency load coil, and takes that argon and ionizes it. So now we move from gas, being argon gas, to ionized gas with a lot of ions and electrons. And the plasma is generated and it's very, very hot. Very high temperature. Does that answer? Yeah. Okay. Good. So that question related to this imagery. Good question. All right. Now, we talked about sequential, so we can measure several elements in sequence. If I have 1 PMT, I can measure simultaneously 7, 8, however many PMTs I have in my unit, or I can use an Eshel spectrophotometer. So an Eshel spectrophotometer has either charge induction device or charge coupled device. Don't worry about remembering that. Remember Eshel spectrophotometer? It's kind of similar to the concept of a PDA, photodiode array. So what this detector does is you get the light emitted from your sample through the plasma, and then it goes through a prism and grating system, and the light gets broken down into multiple wavelengths, and all the wavelengths reach the CID detector, and you get simultaneous reading of all of your elements, basically. So it's very, very efficient, but very expensive. Okay, so here you can detect elements, a larger number of elements than the instruments with PMT. Okay. So all you need to remember is the name of that detector, Eshel spectrophotometer, and then you diffract the light, and all of that diffracted light, different wavelength, reaches the detector. They reach the detector, and you get simultaneous reading of a very large number of elements. But it's very expensive. We don't have it here. I think we have ICP in the soil department, where they measure elements in the soil frequently. I'm not sure if they have Eshel detector or multiple PMTs. So it depends. If you have a lot of samples and you need a lot of throughputs and a lot of element, it might be a good investment. So now I want to spend a little bit of time, talk about how you prepare your samples for analysis for atomic absorption or atomic emission. So those of you that did the lab, you received little crucibles that had ash in them. So these porcelain crucibles, we weighed sample in it and we put it in a furnace to burn off organic matter or incinerate, oxidize. So all organic matter gets oxidized and what is left is the ash, inorganic matter. In it, you have those elements of interest. We call this dry ashing. Wet ashing, which I will talk about in more detail when we cover minerals chapter, but here we combust or oxidize our organic matter using concentrated acid at lower temperature that doesn't go into the furnace. Wet ashing is commonly used for iron and zinc and other volatile elements. Especially if we want to report it on the nutrition label. So what we did for you in the lab is dry ashing, combustion at high temperature in a muffled furnace, or inorganic matter remains, and in that inorganic matter, you have your minerals. So sometimes you can do direct injection. You don't have to combust. And this is in samples that doesn't have a lot of organic matter. So let's say oil. You can actually get oil directly into the flame and just measure the elements. But most food, you need to do the ashing, the removal of organic matter before you can measure the inorganic minerals. So what you did, or most of you did in the lab, you prepared blanks. We always prepare blank because we use reagents like HCl to dissolve our ash. That HCl might have contaminants of elements in it. So you always run a blank, you get the crucible that has nothing in it, and you treat it and prepare a sample as if you had ash, but you use those reagents and you run a blank so that you can correct for any contamination. And of course, for quantification, we run standards and very, very pure standards to construct a standard curve in order for us to quantitate. Standards of calcium, over 99% pure, iron over 99% pure. And then the glassware, everything you use in the lab for determination of minerals has been acid wash. So we take all of the glassware, the beakers, the volumetric flask, everything you use is acid washed so that dissolves any minerals that could have been contaminating this glassware before you use them for a lab. So part of overestimation could be contaminated glassware. Part of, and we'll talk about the HCl later on. Why do we use HCl? Because it helps to prevent binding of the minerals to the glass or to the plastic container. Okay, so that's a good stop. Gets me to recap questions for next time. We'll continue on Wednesday.